Welcome back to the next concept under permutations, and this is a concept on not all distinct objects. So previously, for the past four concepts, we have been talking all about distinct objects, right? For example, A, B, and C, right? But let's say I have A, B, and C, then how many ways are there to arrange them, right? With replacement, without replacement, so on and so forth. But in this context, right, now we're going to be talking about something slightly different. What if all objects are not all distinct, right? For example, let's say I have, okay, a very classic case, right? Or maybe let's just put it this way. Let's say I have a word called apple, right? A-P-P-L-E. How many different ways are there of arranging the alphabets? So many ways to arrange the alphabets. Now, of course, you might be thinking, isn't it just, 5 slots, 1, 2, 3, 4, 5? Then isn't it just 5 factorial? Because I have 5 times 4 times 3 times 2 times 1, right? Isn't it this simple case? But the constraint of the question is that even though I have 5 objects, right? You can see over here, I have 5 objects, 1, 2, 3, 4, 5. You realize that these two objects over here are exactly the same, right? You can see that these two p's over here, I'm just going to write it here. So you can see that these two p's are identical, right? So what that means for us, right, is that let's say if I put this p over here, then let's say I put this p over here, right? It will be exactly the same if I put this p over here and then I put this p over here, right? Even though to us is, I'm putting the two different, so-called the two different p's in two different positions. But at the end of the day, it's still pp, right? It's still the same thing. So how do we actually compute this? So, you might have learned this other ways, but how I simplify things for myself a lot is by thinking of it this way, right? So the first one I will do is that I will first treat them as all identical. Okay, so I'll treat them as all distinct. So the way I like to think about it, the first step is I treat all of them as distinct, right? Based on what I said earlier, right? So if I treat all of them as distinct, that means over here I will have 1, 2, 3, 4, 5. Let me see, I have 5 times 4 times 3 times 2 times 1, right? And then this will give me 5 factorial ways to arrange them, right? But then, of course, we know that they are all not distinct because the two p's over here are the same. So we identify the identical objects, right? And in this case, how many identical objects do we have? We have 2 identical, right? So if I have 2 identical p's, then the next step would be how many different ways of arranging these 2 identical p's. These 2 identical p's, right? If I have 2 identical p's, how many ways are there of arranging these 2, right? It will just be 2 factorial, because if I have 2 slots over here for the 2 identical p's, the first p will come here and then the second p will come here, right? So we start off by treating all of them as distinct, but the reason why we need to perform these 2 steps over here is because we now need to divide away all the so-called same permutations, right? Because as I mentioned earlier, there can be a case of PP over here or, the other arrangement, which is still PP, right? So for example, if this is P1, let's say this is P2, then this could be P1 or P2, or it could be P2 and P1, right? So we know that wherever the 2 P's are, there is 2 possible arrangement, P1, P2, or P2, P1. But at the end of the day, to us, it's just PP. So from the 2 different arrangements, we need to divide away the number of ways of arranging them in order to get to just one arrangement at the end. Okay, so this is by far one of the most difficult concepts to grasp at the start, but it just needs time and practice to get used to it. So all in all, the total number of ways would just be 5 factorial. This is under the assumption that we treat all of them as distinct. Then we divide away the number of arrangements that we could have or by arranging these 2 identical p's. And therefore, the final answer to this would just be 5 factorial divided by 2 factorial. And that will give a value of 5 factorial divided by 2 factorial, which will give me 60 ways. Okay, and the general formula for this whole concept over here, I'm just going to write the general formula over here. General formula for n objects that are not all distinct, it would be n factorial over n1 factorial, n2 factorial, where n1, n2 represent the number of distinct objects respectively. So if this concept does not make sense to you yet, it's completely normal because we're going to be tackling a very standard question that tests you on the concept of permutations, but not all are distinct objects. So feel free to pause this video to try out this question over here. And if not, I'm going to be assuming that you're done, and let's just jump right into this question over here. So we want to find the number of ways that we can arrange all these alphabets, right? And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different alphabets to be arranged, right? So you can imagine I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 10 different alphabets over here. But the thing is that we have a couple of alphabets that are identical. For instance, we have the S. So you can see I have S, right? Wait, there's also another T here. Yeah, there's 3 T's. So T, A, I, and then there's a double I, right? There's a double I, and then there's an A, and then there's a C. So of course, you know that the formula for this is just your n factorial, your n1 factorial, n2 factorial, right? And then all the way, right? Depending on how many alphabets that you have identical, right? But again, how do we derive the answer using common sense over here? So the first case, right? The first step, you can try to visualize this as treat all as distinct, right? When you treat all of them as distinct, given that you have 10 different alphabets, you will have 10 factorial ways of arranging them, right? Because in your first slot, you have 10, then the next one 9, then 8, then all the way, right? They don't repeat. Then number 2, what are your distinct groups? So you know that you have 3 distinct S, right? You have 3 distinct T's, right? And 2 distinct I's. So let me just give you an example over here, right? 1, 2, 3, 4, 5, 6. Okay, maybe I need to make 6, 7, 8, 9, 10, right? Assuming, let's say I arrange them in this one specific permutation, right? So this is specific permutation. So let's say I'm going to be labeling them as S1, S2, S3, 1, E2, E3, I1, I2, right? I1, I2. Let's say I arrange them as S, A, T, C, I, E, T, S, I, S, right? Let's just say I arrange them this way, right? Where I still have 1, 2, 3 S's, right? And then I also have 1, 2, 3 T's, and then I have 1, 2 I's, right? So everything fits. Now, in this context over here, right, it seems like there's just one specific permutation. But then you realize that this could be S1, S2, S3, right? But it also could be the case whereby here is 2, S1, S3, right? And then it also can be the case whereby, let's say this is 3, then this is 2, then this is 1. But it doesn't matter whether it's S2, S3, like it really doesn't matter whether it's S3, S2, S1, or S1, 2, S3, or like S2, S1, S3, right? So on and so forth, right? It doesn't matter because what we want to do is that we want to view all of them as just S, right? We don't care whether it's S1, S2, S3, or so on and so forth. So how do we actually eliminate this and just view them as just SSS? The way that we actually view them is that we need to first count how many different ways or how many different so-called possible arrangements are there, right? And from here, we know that for S1, S2, S3, from this over here, we got 3 factorial different so-called arrangements, right? It can be S1, S2, S3, S3, S2, S2, S1, right? There's a 3 factorial different arrangements. And then same for the T, right? This is the T1, T2, T3, but we know that it could be the case of T2, T3, T1, right? But we don't care. We just want TTT. So we know that for T1, T2, T3, once again, there are 3 factorial different arrangements, right? There are 3 factorial different arrangements. And then same thing for your I, right? I1, then I2. Right, I1, I2. These two over here, you have 2 factorial different arrangements because it can be either I1, I2 or I2, I1, right? But at the end of the day, we don't care whether it's S1, S2, S3, S3, S2, S1, right? We just care whether it's SSS. So the third step will be to divide away all the identical permutations, right? So we know that out of the 10 factorial different arrangements, right, we need to divide away the 3 factorial different arrangements that come from the S, right? We also need to divide away the 3 factorial that come from the T. And we also need to divide away the 2 factorial that come from the I. So all in all, the answer to this, when you key this into your calculator, you get a final value of 50400 ways as the final answer to this question over here. Okay, so this is a very classic question that you realize that in your own practice, you will encounter a lot of this. Subsequently, I hope that this made sense to you. If not, let's just try the next question over here. And same thing, pause this video to try this question out. If not, we will tackle this question together right now. Okay, so let's just jump right into this question over here. We got a bag that contains 5 red and 3 blue tokens, all which are identical in about color. So 4 tokens are taken out of the bag and ran without replacement and arranged in a row. How many ways can this be done? So let's just draw this out, right? I got 5 red, and 3 blue. So blue, blue, blue. They're all identical, and then now we take out 4 different tokens. 1, 2, 3, 4. Without replacement means I don't put them back in, and at the same time they are arranged in a row. That means in this context the arrangement matters. So how many ways can this be done? So in this case over here, right, there are a few different cases, right? And in this video I'm going to teach you this method, right? The method over here is called grouping by cases. Because in this context, right, we can actually count the different number of possible cases, right? And case 1 would be a context of 3 blue and let's say 1 red, right? You can have case 2 also, which is 2 red and 2 blue, right? And the case 3 would be 4 red and 0 blue, right? And the last case over here would be your 1 blue, right? And also 3 red, right? Let me just tie this up. So here I have red, 3 red, 1 blue, and then 1 red, right? So you can see that there are 4 different possible cases that you can physically count. So in questions, sometimes it might be a little bit more beneficial for you to just physically count all the different cases. So in this context, right, let's say if it's 1 red and 3 blue, this over here is already fixed to the case, right? So in this case 1 over here, we know that we already have 1 red and 3 blue. So we already know that our sample size to begin with is 1 red and 3 blue. So how many different ways are there to arrange this 1 red and 3 blue? And the number of ways to actually arrange this 1 red and 3 blue would be 4 factorial over 3 factorial, because over here I got 4 items and 3 of them are identical, right, based on the formula that we have discussed earlier on. Now for case 2, right, it's also already fixed, right? I have red, blue, blue. So how many ways are there to arrange them? You have 4 factorial because there's 4 items, but we need to divide away R1, R2, R2, R1. So it's 2 factorial. Same thing, B1, B2, B2, B1, we need to divide them away, right? If it's 4 red, right? How many different arrangements are there? It's simply just 1, right? Or you can view it as 4 factorial. You arrange the 4 different R's and then you divide away the R1, R2, R3, R4, right? Which is just 1, right? And we can immediately just jump to 1 because R is literally the only possible permutation, right? The only permutation given that they are all identical. Last but not least, you have 3 red and 1 blue. So red, blue. So to arrange this, we just need 4 factorial because I have 4 different items, divide away the identical of 3 factorial, right? And when you add up all the different cases, so case 1 plus 2 plus 3 plus 4, you end up with a value of 15 ways as the final answer to this question here. So in this video, you have learned a method of grouping by cases that allows you to tackle questions like this, whereby the distinct cases can be physically accounted for, right? And with that said, that brings us to the end of this question. Before we actually tackle the next concept, let me know if you have any other questions in the comments. If not, I'll see you in the next video.